Good evening, everyone. A warm welcome to everyone present here. We are going to start the webinar in 5 minutes. I would like to welcome today's speaker, Mr. Krunal Kheraiya, sir. We also have with us Mr. Siddharth Vyas. Uh, Siddharth, can you just please introduce, sir, and then we can move forward with the webinar.
Yeah, am I audible?
Yes, you are audible.
Yeah, good evening, everyone. Rather, good afternoon, everyone. I'm Siddharth Vyas. I'm a design engineer at Shailendra Semi. Today, I'll be introducing our speaker for today, Mr. Kunal Khiraiya. He is a professor at Gyan Manjari Institute of Technology. He has conducted 17 expert talks.
Hello. Yes, Siddharth, you are not audible, I guess. Hello. Siddharth, you are on mute, I think. Kindly unmute yourself.
Okay, am I audible now?
Yes, audible. Please go on.
Yeah. Hi everyone, I am Siddharth Vyas. I'd like to introduce our speaker for today, Mr. Kunal Khiraiya. He is ME Thermal Engineering, having 10 years of educational experience in academics and 3 years of industrial experience. He has conducted 17 expert talks, has published 19 papers internationally and nationally. So this was a short introduction to our speaker for today. I'd like I would like Kunal Khiraiya sir to just start his presentation and enlighten us with his knowledge. Sir, please.
Thank you for the introductions. So now,
Can I get just a minute? So please, sir. Before starting the presentation, I would request all the participants to please mute themselves. Please, if you have any questions, you can write them on the chat. We will take the question answers round at the end of the seminar, right? Fine. Sir, please continue with the presentation.
Okay, so first I would like to thank the Asia Ahmedabad chapter for giving this opportunity to me to present something about cooling towers in front of our good audience. And I also congratulate the student activity chair of Asia Ahmedabad chapter for organizing this kind of wonderful webinar series, which is going on since last so many days. And they're providing the good knowledge to the students as well as industry experts and all the participants who have attended that webinars. So first, I will introduce that why I'm selecting this topic. I select this topic when I present in the one meeting of ISRA Ahmedabad. At that time, we are deciding that in upcoming webinars, what topics that we are selecting so that it can be directly benefited to our pre-final and final year students when they are going directly into the industry. This kind of the knowledge is very helpful at the beginning level. So idea came into my minds that in curriculum of GTU as well as so many different university, the depth study about the cooling tower is not given in the curriculum. And in many of the industries, mostly they are utilizing the cooling tower as a one of the utility in their plant. I also face this problem when I entered, when I'm completing my graduates and I start my professional career journey with Excel CropCat, and I have faced to look after the 7 different cooling towers. So the story is behind selecting this topic is just like that, whatever I'm telling. So now I start my presentations. Now it is visible. My screen is visible to all.
Yes, sir.
Yes, sir. Visible. It's visible.
Okay. So as it is mentioned in the flyer that what are contents that I am covering in the today's webinar. That first is basics of cooling tower, selections of cooling tower, some of the factors which is affecting for the selections of cooling tower. Then we are going with performance assessments, different case studies, and energy saving opportunities in the cooling towers. So this is a basic content that today I covered in my 1 hours of talk. So let us start. But before starting the today's sessions, I have I have to give some instructions to our attendees that I have as an academicians. I have managed these presentations. After certain slides, I have set some knowledge checkpoints. So you can use the chat box for interactions. And whenever I have a chat box, means I have the slides of knowledge check. At that time, you can interact with me by using the chat box. As well as I request some of the points, that is some of the points are very important in these presentations. So you can use a pen and paper to note down that as a takeaway points from this webinar. So let us start with the first slides. So basic, I'm starting with the basics, refrigeration cycles. All of us are very familiar with the cycle, and there are 4 components, as all we are know that VCRS systems. But focus in this slide is to focus over here, the condenser portions. So in condensers, basically the heat dissipations means a heat rejection from the cycles are happening, and we are using water cooled or the air cooled condensers for rejections or for absorbing the heat from the our refrigerant. So now first checkpoint, I'm having a two different figures. So please audience, please use the checkbox. Here I have a knowledge check, that is a name of the following components. So I have two different components in the slides. So first one, which component is that? Please interact with the help of chat box. Some of says is the cooling coil. Some is called as evaporator. Some is called as condenser. Yeah, heat exchanger. Okay, you can use the context of previous slides. Urvesh Chauhan is saying condenser. Yasha, condenser. Condenser, yes, absolutely it is condenser, but of condensers. Which was the cooling medium we are using with this kind of the condensers. I'm not having a perfect answers receiving right now. It is fin tube condensers, yes. Yes. Viral Gandhi saying correct answers. Viral Gandhi, I appreciate your answers. It is a condenser, but basically it is a air-cooled type of condensers. Means here the cooling media we are using is a air-cooled. Now second component. Please use the chat box to interact with me. Second is also condensers. Sandeep Patel is saying over here, condenser. Yes, it is correct, condensers, but I need some perfect answers. Shuvam is saying water cooled condensers. Yes. So there are two types of condensers generally we are using whenever we have heat ejections from the VCRS systems. So now we are discussing the requirement of cooling tower. Why the cooling towers are required? First, my questions is why cooling tower is required. So in the refrigeration plant, we discussed that heat dissipated in the condensers. Cooling medium used, it is maybe air or water. If air is used as cooling medium, then the heat transfer coefficient is very low, because heat transfer from one medium to the another medium. Both mediums are gas, and due to which the heat transfer coefficient is very, very less, and we require a larger surface area to accommodate our heat rejection process. Now next, in high capacity plant of the refrigerant, we are used the water cooled condensers. Then air cooled condensers is economic up to the 5 to 6 degree of atmospheric air. Means if you want to do the heat rejections below 5 to 6 degree from the atmospheric tribal temperature of air, then obviously air cooled condenser is very economic. But when you are going lower than that, means if you are moving towards downward directions, that 7 degree below the dBT of atmospheric air temperature, suppose 7, 8, 9, then the compressor work may get increases and you cannot get the efficiency. So we use water cooled condensers, and water cooled condensers is work below 5 to 6 plus 3 degrees centigrade from the dBT, and with having a 10% of saving in compressor work. So this is a benefit we are getting in the compression work, and it obviously affect overall performance of an refrigerant plant. So now we are going to look about the layouts of refrigerant plant of higher capacity with water cooled condensers. So here in this figure, load is there. It is represented with the pink color box. We have chilled water pump. So this is a secondary refrigerant we are using as a water over here. which is transferring heat from load to evaporators. And main cycle, our vapor compression cycle is shows over here. And the condenser, which is the water cooled condenser, obviously, because our plant is having a high capacity. So here blue line is show water which is coming at low temperatures, which comes out as a high temperatures from the condensers. So every time we need a low water to absorb the heat from the condensers. So how we can generate the every time the low water? So for that we need this additional devices, and that device is called, and that is our focus of today's webinar, that is a cooling tower. So here we are using the hot water, which is comes from the condenser. It is going on the cooling tower, cooled down, and heat is rejected from hot water, and it is absorbed by the air, which is comes from the atmosphere. And again, we get the cold water. So this is a cycle, and this is a layout of plant, and that's why we require the cooling tower in different plants and refrigeration systems. Now, cooling tower. So we go first, whenever we heard the name, the cooling tower, first pictures comes in our mind, that is looks over there in the screen. And today's whatever we are discussing, the first one is a natural draft cooling tower, which is widely used in the thermal power plant. The second one, which is called as different types of packed cooling tower. Again, we learn the classifications in upcoming slides, so I'm not giving much time on this slides, and we move forward, and further slides later on we are discussing the classifications of cooling tower in upcoming slides. As cooling tower is applied in process cooling, condenser cooling, jacket cooling. Jacket cooling is in some chemical industries, they have required jacket vessels for doing that process, and that may be a heating process, it may be a cooling process. So we need to supply the heating and cooling utilities, and it is required for the process. Then AC and chilling plants, then heat exchanger, obviously, plastic molding machines, cold storage, gas fire cooling systems, diesel set, captive power plant, air compressor, gas compressor, vacuum pump, and vapor absorption machines. So these are the few of the applications I have listed over here in the slides. Now we are for the classifications, for understanding the basic terminology of cooling tower. We are going in classifications. So in classifications, I have divided cooling towers based on the different criteria in a 4 group that we discuss one by one. Group 1, and the criteria for the classification is a method of heat transfer. So method of heat transfer is wet cooling tower, dry cooling towers, and the fluid coolers. Wet cooling tower means the water basic science of the heat transfer method is evaporations of water is take place, and the air which is comes from the atmosphere are carry the some amount of water, and the heat exchange will be done between the air and water. Dry cooling tower means there is no evaporations are occurs, and we achieve the cooling of water. Then third one is fluid cooler. I want to say that here the dry cooling towers and fluid coolers are the special applications which is used in chemical industries. In chemical industries, we need to cool down some special kind of fluids. It means some acid, sometimes we have different substance which is not exactly water. So other than the water we are using, because once if we have a chemical and it will be evaporated, so it is going in the environment, and it has some hazardous effect. So whenever we have chemical industries and we have this special applications, at that time we are not utilizing the dry cooling towers. We are using the dry cooling towers and fluid coolers. We are not using the wet cooling towers. Wet cooling towers are used in the DG set, in HVAC systems, in the power plant. We are using the wet cooling towers. Then third, it is based on the air draft. Air draft means the pressure difference between the tower and the atmospheric pressures of air. So based on the air draft, we have classified the cooling towers into three categories: atmospheric tower, natural draft tower, then the mechanical draft. Atmospheric towers means it is only one kind of cube, and there is no any kind of the shape change are there. So it means there is no pressure difference is created. The draft is actually, we can say that it is near to zero, because only the atmospheric pressures are there inside the cooling towers and outside the cooling towers. So this kind of cooling towers is called as atmospheric tower. Then second one, the second cooling second type is natural draft cooling towers. In natural draft cooling towers, we have generated the draft using the our structures, different kinds of structures. As we see in the first slides, that there is a one chimney type and hyperbolic cooling towers are there. So these kind of cooling towers, it is comes under the natural draft towers. Third is mechanical draft. Mechanical draft means we are applying some amount of mechanical devices, and due to that, the air circulations is generated. So mechanical draft is further classified into the two groups. One is the forced draft, and second one is induced draft. In forced drafts, the air means moving from bottom to top, and in induced draft, it is also moving from bottom to top, but the positions of the fan is different. In forced draft, the fan is located at the bottom of the tower, means it is near to the lowers, and in induced draft, the fan is located at the top of the column. So now we are moving towards the third classifications, and third classifications is based on the air patterns. So air pattern, it is cross flow and counter flow. So it is based on the interactions between the air and water. So whenever it is cross, it is coming in cross, it is called as cross, and counter means it is in opposite directions. Water is flowing from upward to downward, and air is moving from down to up. That is called as the counter flow. Then fourth group means the classifications is a build type. Package means it is packed and you just have to install over the locations or in the industries. And second one is field directed. Field directed means you need to assemble the different parts at the locations when particularly you want to install the cooling towers. So it is classifications of cooling tower. Now constructions. We are going in the constructions. So I have kept the two figure over here. One is very cut section figure. So we move in the cut section figure. The first one is the part which is shown over here on the top. It is called as a motor, which runs the fan and the blades, and then yellow color part you can show there is eliminators. Then main important part, that is a main header pipe, and it is also combinedly called as a water distribution systems. Then here blue colors of some portions you can see in the figure, that is called as a PVC field, or the different materials are used for the field. Then you can go over here, there is a lower guard which is having for the uniform distributions of airflow from the bottoms. Then on the bottom part, it is a drain pipe and the water basins are there. And lastly, there is a on which we erected the cooling tower. It is called as a structures, and generally we are using the RCC pillar as a structures. So now we list down, we have listed down the various component of cooling tower. So casing, then very important, air inlet and air outlet. So air is coming inlet from the lower, and air outlet is eliminators and from the discharge of fan. Then fan itself, drift eliminators, it is located just lower the fan. Warm water inlet, it means water distribution systems is comes with a header and nozzles. Then water distribution systems. Then packaging, we see the different types of fields that we are using. Cold water basins, that is located at the bottom, and the cold water outlet. So these are the important components of the cooling tower. So now all we are familiar with the basic terminology which is used, as well as the different classifications of cooling tower. So now I just touch upon the one topic, that is a heat exchange process is happening in the cooling tower. Actually, it is a very important topic who wants to learn more on the cooling tower, because this fundamental is required for a design of cooling towers. But I am not going in depth of this topic because it requires a larger amount of time, and also it is not matched with my title of the topic. So if audience wants this topic, so we can later on, we are also arranging a one webinar on the designing of cooling tower. So now fundamental, I've kept one figure over here, which shows different parts. Fan, then hot water in, there is a water distributions, then there is a surface exchange surfaces, the fields we are using, then air, which is comes from the water. So now we go in the depth, somewhat depth. I'm just touching upon this concept of heat exchange and how the model was developed for the cooling tower heat exchange processes. So we start from the water distribution systems. So you can see one figure over here. The from header, the water comes in the nozzle, and nozzle, what is the functions of nozzle? Nozzle, it works as atomizing devices over here, which converts the larger liquid droplets into the smaller drops of the water. So basic process happening in the nozzle is atomizing. And atomizing, it means expansions, and whenever the pressure drops are occurs, the temperature is linearly proportional to the pressure. So as pressure is going down, your temperature is going down, and waters means a droplet which is comes out from the header, obviously it drops some amount of temperatures. So now after this process, I'm not going in depth of that. I just touch upon this phenomena which is happening over here. So the in nozzle, it is atomizings are happening. After atomizing, the droplet which is comes in the environment of air, it exchanges the heat from the surfaces, and finally we get here the evaporations process of water droplet. And there are many models are available for the calculations of the coefficient of heat transfers, as well as the droplet evaporations, droplet radius. A famous model, that is a d-square law, is very famous, and it is applicable over here in this process of heat exchange. So heat is transferred, water droplets are evaporates, and finally water gets at lower temperatures. Here, if anyone is interested in very depth of this heat exchange process, as well as the designing of heat exchangers or the method of analysis, then one can go with this different modes. Merkel's theory is there, which is coming in 1925. After that, Popes is there. There is another scientist which is comes in later 19, and most famous method, that is effective NTU methods, that is number of transfer. One good articles is also available if one wants to refer the this phenomena. Then Raji Panikkar, and it is author of this paper, and this paper and article it available on the ISHRE websites. It is published in August 2016. So if one can interested, then definitely go with this article. So I cannot going in depth of this knowledge. I just stop myself over here in the heat exchange process because it will take a too much amount of time. So now one should, when we have know the different parameters, and if we want to design the heat exchanger, means a cooling tower, then what are the design criteria that we need to keep in our mind? So first and very important criteria, that maximum amount of contact that should be happens between the air and water. So it can take a time, and with the help of time and the contact area, interfacial area, it has a larger amount of heat transfers, and you get a lower amount of cooling water temperatures. So for that, you need to provide the packing and the good water distribution systems that is required for the maximum contact between the air and water. So which is very most important criteria. Then second is airflow distributions. If your flow of air is not uniformly distributed in the surfaces of the cooling tower, then you definitely not achieve the good rate of the heat exchange. Then minimum water loss causes from the spray. Yes, water conservation is very important. Later on, we also discuss what are the criteria are there, water losses. Then considerations of space limitation. Yes, very important design criteria or design aspects. Then dimensions of tower. Yes, with considerations of the tree. Means what temperature the water is coming in the cooling tower, what temperature you need to supply it again, as well as the outside air conditions, means WBT of outside air. These are the three important criteria. And with respect to that, you need to design your tower. And last is important, very important, quality of water or the fluid which is available for the cooling medium. Then selections, yes, very important, selections of cooling tower. To select the proper cooling tower from the rating of the table, for the following data must you know. Yes, so actually most of the time industry people are not going in designing of the cooling tower. Instead of that, they are going for selections of cooling tower. So selection of cooling towers are a very important task. If you select the improper designs or the improper model of the particular cooling tower, then obviously it cannot be matched with the energy requirement. And if your matching is not there, then obviously you have a loss of efficiency. So very important and critical task is there for the selections of cooling tower. And for the selections of cooling tower, you must have to collect this much amount of data before selections of cooling tower. Cooling load, what cooling load you need to serve for the different processes. Then weight by temperature of air. Yes, what temperature you are looking as a cooling water out comes from the cooling tower. What is your water entering temperatures? Then flow rate. Yes, flow rate over the tower. Here I am mentioning L by S. It means how much amount of quantity that is reserved with you so that you can have the evaporations from the water is take place. If you have scarcity of the water, then this is very important portions, or this is a very important factors which can affect the selections of cooling tower. And last is very important, space availability. So it is very important, space availability. Now we are going for next, how you select the data. So with the help of this data, which is available, you need to go with one catalog of different suppliers supply. So here one is important table which is given. So if you look over there in the table, the type is there are wet bulb temperature is given, then the medium temperatures, high temperatures, and low temperatures. Then there is a model number is given. So using this table, you can first table you can select the tower. And then with the help of second, I'm not promoting any manufacturer over here, because I'm not having any kind of the things. Just for the sample how to select the cooling tower, I'm selecting this our two tables, so our audience get idea how to select the cooling towers. So using this kind of selection table, with the help of the data which is available with you, you can select the cooling towers. So that is and for this cooling tower. So up till now we are discussing about basics of cooling tower, then different heat exchange processes happening in the cooling tower, then selections of cooling towers, design criteria. So now the most important part of the presentations are starts. So the operating parameters means measure parameters. Now I'm starting to discussions about the performance assessment of an cooling tower. So be careful and be note down if you required some of the important parameters that we are discussing. So suppose as an engineer, you want to do the energy audit of a cooling tower. So what kind of parameter you need to measure? So here I'm giving the list. That first and important is wet bulb temperature of an air. How you measure the wet bulb temperature of an air? You can use the checkbox. You can use the checkbox, please. How you measure the hello. Yes, Psychometer, which type of psychometers? Yes, slings. Okay, okay. Yes, good answers. Hitesh Kumar, yes, giving the psychometers. Okay, so psychometer we are use sling psychometers generally famous. So we are using these devices to measure. Second is drivable temperature of air. Both are measured simultaneously using these sling psychometers. Then cooling water inlet temperatures. Which kind of device is used? Please, audience, respond. Cooling tower inlet water temperature. How you measure the temperature of cooling water, which is comes from any kind of heat exchangers or any cooling means a chemical jacketed vessels or any heat sources which is supplied the cooling waters. So how you measure? We use the RTD or different types of the devices for the cooling water temperature measurement. Yes, I get the response. Yes, Bhavin Makwana, temperature gauge. Yes, RTD. Yes, very good. So using these different temperature devices as per the requirement of the your resolutions, you can use any kind of devices. A PT100 is also one good sensors which is available with a 4-wire to measure the temperatures. Then exhaust air temperatures, electric readings of pumps and fans motor. Then water flow rate. Yes, very important. How you measure the water flow rate? Audience, how you measure the water flow rate? Flow meter. Yes. Orifice meter, Smith Gadia, yes, good. Neeraj Patel, rotameter, yes, very good. But in industry, these are the not devices are used. Yes, flow meter, yes. Then Venturi meter, Viral Gandhi is saying, yes, I is also saying that Venturi meter, no, you cannot use this kind of devices because it is a closed types from pump curve with the pressures. Jigar Patel from pump curve. Okay, no. Rotameter. Repeatedly, I get the answers. Some of the say is a pitot tube. No. Anyone? Yes. N.T. Rana says ultrasound. Yes, very good. Whenever you don't have any access to measure the fluid in contact with that fluids, then we use the ultrasonic flow meters. Yes, ultrasonic flow meter is used for a water flow rate measurements. Now airflow. How you measure the airflow rate? Please, audience, response. How you can measure the airflow rate? Orifice. Okay, nanometers, yes, correct. Anemometer, yes. Anemometer is used for the measurement of a velocity of gas and from particular duct with the help of area. As all of you know that Q, that is a rate of discharge, equals to area into the velocity. So by using the anemometer, you can also measure the velocity of the air and you can have the airflow rate. Okay. So this is things, and I think all of you have clear in your mind that how to measure and what are the different parameters are required for a performance assessment. Okay. Now the next task after this gathering of the different parameters, what are the different performance parameters are there for a cooling tower on basis of which we can reach to the some conclusions. So now I'm going in the performance parameters. So different performance parameters are there, and it is the cooling means range of cooling tower, approaches, effectiveness of cooling tower capacity, evaporation losses, cycle of concentration. Yes, someone is asking about the evaporations in earlier time. So we will later on come again on the COC. It is very important points of discussions in today's presentations. Then blow down losses, and very important, liquid to gas ratio. So these are the performance parameter on the basis of which we can check out whether our cooling tower is performing well or not. Now we are going in depth with the different performance parameter. So for understanding of the range, I have kept one figure over here.
hot water, which is comes from the any heat load, which is shown over here by the red line. The blue color, light blue color, this is cold water temperatures, which is comes out from the cooling tower. So it means this much amount of temperatures are decreases in cooling tower. And last one, very dark blue line. Dark blue line is show the wet bulb temperature of an air, which is comes from the atmosphere. So what is a range? So it is shown in figure. The range is the difference between the cooling water inlet temperatures and cooling water outlet temperatures. And if you have a high range, then you can show definitely, because it is a performance parameter. So after measurement of a performance parameter, you need to conclude some things. So here, what is the conclusion from the range? If your cooling tower has a high range, then we can say that it is a good performing cooling tower. Now, next is approach. Again, I'm using the same pictures or the same schematics. So here, the difference between the light blue and dark blue is called as a approach. So low approach is good. Yeah, see here, it is a reverse of that. In the range, if your range is high, then your performance is high. If approach is low, your performance of cooling tower is good. So this is a difference between range and approach. Now effectiveness. Effectiveness is always expressed in the percentage. It is equals to the range upon range divided by the range plus approaches. Audience, please ready. Knowledge checks are coming. So you can have a percentage. It means 100 into range upon the approaches. And here we have conclusion from the effectiveness calculations that high effectiveness, it indicates good performance. Then cooling capacity. Yes, suppose cooling capacity. So cooling capacity is very important term, because whenever the students comes from the graduations into the industry, they even don't know the capacity of cooling tower measures in which unit. So cooling tower capacity is measured in the tons of refrigerant, or you can express this capacity of cooling tower in kilocalorie per hour. So these are the two different units. How you calculate? Mass flow rate of water, specific heat, Cp of water, and the temperature difference. It means simple formula, whatever you are using, MCP delta T. High cooling capacity, it means a good, means high cooling capacity with the reference to the rating capacity of cooling tower which is installed. So suppose you are installed the cooling tower of 200 TRs, and you are near to 200, means you are near to the 195. So your efficiency utilizations is near to 92% or more than that. So you can say that the performance of a cooling tower is good. Now, knowledge check. Audience, please use the chat box. Here I have taken one observations. The cooling tower observations at industry site where the cooling tower flow rate is 5,000 meter cube per hour. Cooling water inlet temperature is 42 degrees centigrades. Cooling water outlet temperature is 36 degrees centigrades. Wet bulb temperature is 29 degrees centigrades. What is the effectiveness of cooling tower? Yes, audience, use the check box. Hello. Audience, use the check box. Yes, Bhavin Makwana says a 53% of effectiveness. Okay. Ajit, Mr. Ajit is seeing that 46.1. Mehul Jadeja is also saying 46. Okay. Alpesh Kumar Patel 46. Smith Gadia 47. Yash Shah 51. Sandeep Patel 46. Okay. More response. Rohit Kumar 46. Sachin Kamboya says 46. Jigar Patel 57. Okay. So effectiveness for the calculations, okay, Hastiv Shah is saying 51. Sashidhar is also saying 46. Alpesh Kumar having 46.153 percentage. Okay, good accuracy. Sandeep Siwala 46. Okay, good. Viral Gandhi, yes, is saying 0.4615. Okay, it is multiplied by 100. Okay, 46. Upendra Dubey 47. Okay, okay. So we received the good responses from the audience. So now I have prepared the solutions. So we go on the solutions. Here, first we calculate the cooling tower range, 42 minus 36. So you get a 6 degree of range. Cooling tower approach, that is 36 minus 29, you get a 7 degree. So effectiveness percentage equals to 100 into range divided by range plus approaches. So exactly, yes, I received one of the good answers in two decimal, that is 46 point. Yes, Rohit Verma is also saying good correct answer, 46.15. Okay, good. Now again we are going in a next performance parameter, that is evaporation losses. So what is evaporation losses? Evaporation losses are the losses of water quantity evaporated from the cooling tower for the cooling duties. The theoretically, yes, this is very important parameter because you cannot have directly any formula for the evaporation losses calculations. So here one empirical formula which is largely used in the open literature, and it is I'm taking from the Paris Chemical Engineers Handbook, page number 12 to 17. So 0.0085, 3 times 0.85 into the 1.8 into the circulation rate in the meter cube per hours into the temperature difference. This is an empirical formula. Generally, industry peoples are used for the calculations of an evaporation losses. Cycle of concentrations. The next important parameter is cycle of concentration. Cycle of concentrations, generally it is represented by the COC, is the ratio of dissolved solids into the circulating water to the dissolved solid in a makeup water. Means you need to measure the TDS of a makeup water, means a fresh water or raw water, and the circulating waters. As all of you, we know that after circulations of some time of same water, the concentrations of TDS are get increases, and we need to blow down some of the water from the basin. So whatever the water we treat as a blow down from the basins of the cooling water, cooling tower. So blow down losses, it depends on the cycle of concentrations and the evaporation losses. It is generally given by the relations. So you can calculate how much blow down that we need to give. So here important parameter is cycle of concentrations. Based on the cycle of concentrations and the evaporation losses that you can calculate using the Paris empirical formula, you can be able to calculate what amount of water that you need to bleed from the blow down pipes. Again, knowledge check, audience ready, and use the chat box. It is very simple. In increasing, if you are completely understand the COC, then you definitely will give to the answers of this knowledge check. Increasing the cycle of concentrations, it means cycle of concentrations are increases of the circulating water in the cooling tower, then the blow down quantity will, yes, I have received, yes, Viral Gandhi 100% decrease. Okay, reduce. Okay, Shashidhar, yes, is also called as reduce. Decrease, Hitesh Jani is called decrease. Okay, okay. Very easy and very understand that. So here it is the decreases. Okay, definitely it is understood. Now we are moving towards the most important parameter, performance parameter, that is called as a L2G ratio, means liquid to gas. So liquid to gas ratio is a cooling tower ratio between the mass of water and the mass of air flow rates. Against the design value and the seasonal variations, we required adjustment and the tuning of water and the airflow rates to get a best cooling tower performance and the effectiveness. So it is very important, and by season to season as well as in different operating conditions, we need to calculate the L2G ratio. How we can calculate L2G ratio? So here I'm using very simple equations of thermodynamics, that is a energy balance equations. So mCp delta T, and here I'm using here I'm taking a notations of L, T1 minus T2 equals to G into H2 minus H1. So if I'm making L by G, that is equals to H2 minus H1 divided by T1 minus T2. Here, most important terms and the unit balancings, because generally enthalpy we are measuring in kilojoule per kg from the psychometric charts. H1 and H2 means enthalpy of the air before it is entering in the cooling tower and it is leaving the cooling towers. So we need to measure the enthalpy of air water vapor mixtures at the inlet and outlet. So using the conditions on the temperature measurement by using the psychometric chart, we can able to calculate this enthalpy, and temperature we are measuring. But if you see temperature having a units of degree centigrades, and L2G ratio we are measuring in kg per kg. So here I am treating the units of enthalpy is kilocalorie per kg, and the temperature, so water specific heat is 1. So we don't need to multiply it with the Cp. Otherwise, if you are using the kilojoule units, then you need to multiply it with the Cp of water, that is 4.186 in kilojoule per kg calorie. So here most important terms, please note down if you want to remember it. Otherwise, you can take in the kilocalorie. Now, additional data. Yes, we have listed down the so many data that we need to measure and we need to calculate. Apart from that mathematical calculations at a time of energy audit, what additional data or what additional measurement that you need to do. So I have listed down some of the points. Cooling tower design data curves to be related as a basis. Yes, it means you need to compare that all the performance parameter with the rated one or the design parameters. Process data on the heat exchanger load and the line power plant measurements and room readings, as well as other relevant data. Cooling water flow measurements, either direct or interrupted pump motor kilowatt and pump head, then the flow characteristics curves that you need to measure. Blade angles, obviously, and the most important is TDS of cooling tower. Observations of nozzle, yes, observation is of nozzles, drift eliminators, the conditions of fills, splash bars are important. Case studies. So we discuss about the case study, various case study. So yes, now we are moving on the second last portions of our lecture, that is webinar, that is case study 1. So here I'm taking a big case study of case study 1. Please careful audience, so that you can understand how to entrap the data which can be measured during energy audit and can be comes with some conclusion at the end of the energy audit. Whenever you need to submit the report, at that time you must have to need the some of the conclusion points. So I'm starting with the very first observations. The energy audit observations at a cooling tower in a process industry, I'm not mentioning the name of process industry, are given as below. So here, it is which kind of cooling tower? Audience, please, response. Audience response. Which kind of cooling tower show here? Use chat box. Which kind of, yes, we have learned the classifications. So which kind of cooling tower is that? Mechanical draft, induced draft. Yes, Ajit ji is saying correct answers. That is a cross flow. Okay, induced draft. Okay. I received the correct answers, so many correct answers, and also I appreciate the efforts of the audience so that we can interact in between the sessions. And at session is very interactive sessions with the help of this kind of good response from the audience. Now, okay, good. So now we move further in our case study 1. So in case study 1, we have the energy audit observations. So here we have one heat exchanger. You can treat as a jacketed vessels. So cold water is supplying to the jacketed vessels, and the hot water which comes from the process utility, and it is going in header, which from the header it is sprayed down and it is moving in downward directions. So what are the data that we collected during the energy audit? So cooling water flow rate measurement done with the help of ultrasonic flow measurement, that is 1565 meter cube per hour. Water inlet temperature 44 degree, which comes from over here hot water. Water outlet temperature, it is supply from the pump, that is 37.6. Wet bulb temperature of air mixtures means air temperature measurement using the slim psychometers, that is 29.3. Air flow rate is 989544 meter cube per hours. The density of air, it is also important parameters, 1.08 kg per meter cube. And the COC means cycle of concentrations, that is given as a standard from the manufacturer, and the process operational main over there, which is looking about the cooling utilities, they have maintained the COC of 2.7. So now one by one, we are going to measure the different performance parameter, and from the performance parameter, we can conclude with some comments. Yes, CT flow rate is given 1565 meter cube per hour. So if you multiply it with the 10 to the power 3000 kg per hour, cooling tower fan flow rate, it is given as 989544 meter cube per hour. Density of air is given 1.08. So finally it comes as 1068708 kg per hour. Now important parameters, yes, I definitely say that L2G ratio of cooling tower is very important parameters. So here, using the sling psychometers, we are measuring the wet bulb temperatures of air entering and air leaving. And from that enthalpy we measured by using this psychometric chart. So we get 28.17 kilocalorie per kg, 39.6. Yes, see here the kilocalorie. I said that if you are using a unit of kilojoule per kg Kelvin of the CP, and if you are using the enthalpy unit is a kilojoule per kg, then definitely you have to divide it by the 4.186. So formula again, I revise the formula, H2 minus H1 divided by T1 minus T2. So from that L2G ratio, which is important parameter, that is 1.79. Now moving further, we go for the calculations of range, then approach. The range is our temperatures of water, which comes from the process heat exchanger, that is 44. The water we supplied from the pump, it is 37.6, and the wet bulb temperature of air is 29.3. So we get a 6.4 degree centigrades of CT range, and our cooling tower approach is 8.3. And from CT means cooling tower range and approaches, we calculate the effectiveness, and the effectiveness is comes near about 43.53%. Then how the TR utilizations means, what is the installed capacity of cooling tower and what exactly the TR we are using. So TR that we utilizing, water flow rate is 1565 into the range, temperature difference means a range, into 10 to the power 3 to convert the meter cube into the kilograms. And finally here, for conversion of kilocalorie per hour to the TR, that we need to divide it by the 3024. So finally we get 3312 TR, 3312 TR that we are currently delivering. The evaporation losses, we are using the Paris standard empirical formula, 0.00085 into 1.8 into the flow rate, that is 1565 into the our range 6.4. So finally we get the evaporation losses are happening from the cooling tower is 15.32 meter cube per hour. Then the percentage evaporation losses, it means we need to compare. We have a water flow rate of 1565 and we have evaporation losses of 15.32. So what percentage of evaporations are happening? It is less than 1. So it is good percentage of evaporation losses that we maintain during the operations of cooling tower. Now blowdown losses means a blowdown requirement for the 2.7 COC. So evaporation losses divided by COC minus 1. So our evaporation losses comes 15.32. So it divides by the COC, which is given 2.7, that is maintained by our operation people, minus 1. So finally we get the blowdown requirement is 9 meter cubes are of water per hour is required. Make of water required. Make of water means evaporation losses plus the blowdown losses. It means if you go with the mass balance equations, that whatever the masses are coming out of that mass comes out from the cooling tower, means water we supplied to the cooling tower is our M in, and whatever the M out, we need to balance it. So blowdown losses, which is also comes out, and evaporation loss is also going in the form of the water vapor. So total losses happening of water, it is equals to the evaporation losses plus blowdown losses. So every time we need to have a makeup water requirement of evaporation losses plus blowdown losses. So we need every hour to supply the 24.32 meter cube of the water that we need to supply every times. Then case study 2. An induced draft cooling tower is designed for range of 7 degree. During energy audit, we find the operating range as 4 degree. What could be the reason of this type of situations? So later on, we'll discuss one by one. There may be excess cooling water. If your water circulation is happening at very high rate, so you have less amount of range is there. There may be reduced heat loss from the process. It means your heat supply or the cooling tower duty is also less. Some of the cooling tower cell fan switch off is there. Approach may be poor because of high humid conditions, and nozzle may be chalk. So these are the possible reasons when you get a less amount of range. Now we discuss a case study 3. This is a very important case study because here we are applying a approach of energy conservations and we have good results. Here in case study 3, a process plant installed with a 4-cell cooling tower with a cooling tower fan is of 45 kilowatt. Each cell has operating at 40 kilowatt and at an RPM of 1450. The cooling tower operated at high speed for a 5300 hours, and at the low speeds it operated at 1800 hours in a year. It means a cooling tower means a load on the cooling utilities are vary according to their requirement in the process. It means sometimes it requires run at high speeds, sometimes it is required to run at low speeds. So bifurcations of that running at high speed and low speeds are given in this, or it is measured in the their real conditions. So as a part of energy conservation program, the existing fan motor is replaced with the 2-step motors. Means first case, we have only a single motors and it is running at constant RPM. In second, by the energy audit, we suggest that you have to use the VSD, or you can use the different two steps of the speeds for the motor. So we have this two types of case. Suppose we assume that continuously rotated at fixed speed. So we consume means the 4 fan consumes the 1136 means 11 lakh 36,000 kWh. That much amount of units are required to run the fan. In second case, when we apply the energy conservation program, means we have 2 steps of motor operations. One is at low speeds, one is high speeds. Yes, it is very important over here. 740 divided by 150 to the power 3. From where it is comes? Audience, please response using chat box. Why we have the power of 3 that we are using? Audience. Here, why we need to multiply it with the power 3. Fan at 740 RPM. Fan law, yes. Very good. What is fan law? Which fan law? There are 3 different fan laws are available. So which kind of conversions is there? Yes, definitely I get the good answers. So yes, okay. Vijay Shah is also, Virat Shah is saying of fan law. Yes, the specific speeds of fan is linearly proportional to the power 3. Means P1 by P2 equals to N2 by N1 to the power 3. That is the characteristics law of the fan. So that's why we are multiplying here power 3, and we can get the total consumptions of power is that is summation of both the two 8,48,000. So finally, we achieved the savings of 2 lakhs amount, near about 2,50,000 kWh. Okay. So here I'm showing the schematics. We are using RTD sensors, which comes out of the cooling water pump. And according to the PID controllers, our fan is operated at different speeds. So this is a schematic diagram. Okay. I'm not discussing this case study 4 because time is not permissive. We are also running out of the time. So I'm not discussing case study 4. Actually, I'm just giving the brief idea about the case study 4. Case study 4 is that actual practices we carried out at the power plant. I'm not mentioning the name of power plant because the government resolutions comes in the 2050 that every power plant have a limitations of the fresh water consumptions, that is 3.5 meter cube per hours per megawatt of energy productions. Means if you produce a 1 megawatt, then you need to come only 3.5 meter cube per hours. So these are restrictions that government side comes for conservations of water. So here in this case study, we are having a power plant designs on the COC of 3.8 value, and we suggest the COC of 7 by applying some amount of good heat treatment, means a water treatment plant. So this is how the savings are occurs, and specific water consumption is reduced over here. See, if the power plant is running with the help of with the COC of 3.8, then the specific consumptions is 2.97 meter cube per megawatt. If we go with the 7 COC, then specific power consumption becomes a 2.56. So definitely we have the saving of water. Means this case study is for the water conservations practices in the cooling tower. Yes, last topic of the today's presentations, and I'm only taking 7 to 8 minutes to complete this session. So energy saving opportunities. See, if you definitely all of the listeners are having a good interest in this topic and having a 100% intentions. So I I look that everyone is know about the different components of cooling towers. So different components of cooling tower where energies are interactions happens. So first is fan, cooling water, the heat transfer. So with the help of these different elements of cooling tower, we go one by one. So what is energy saving opportunities are available in cooling tower? So first I'm discussing and why this topic is very famous, because if you are going in industry, cooling tower are the most least maintained utility in the industry. Nobody is taking care of cooling tower because it is not, but then all the peoples are thinking that this is not important utilities, and that's why they are not giving too much importance to this cooling tower. So maybe the power consumption of cooling tower is relatively less compared to other utilities, but indirect impact on the energy consumption of systems to the cooling tower will be high. That's why you need to focus on the cooling towers. Now, we are going in one by one. So first, I have the energy saving opportunities in cooling tower that installed the 2 speeds. Yes, obviously it is in line with the case study 2 that we are seeing. Second is, in oldest day, we have the aluminum or the cast iron fan, means we are using the blade of an axial flow fan that is made of cast iron or aluminum. But nowadays, people are suggesting that you need to use the FRP because it is directly comes in a contact with the water. So corrosion and erosions are there, and after sometimes you need to replace the blades. So we need to change the blade material, as FRP is very a lighter material compared to the cast iron and aluminum. So it helps us to save the energy in the range of 15 to 20%. Then optimize the cooling. Yes, based on the load and the seasonal variations, you need to change the blade angle. So blade angle changing from the characteristics curves which is available for the fan. So based on that, you can save the some amount of energy. Yes. Cases reported where the replacement of metallic or the glass fiber reinforced means FRP, plastic fan blades, have replaced, and FRP blades will have a save near to in the range of 20 to 30%. And if you go for the replacement of these types of fans, the simple payback period is near about 6 to 7 months. Means if you are replacing the fan, old fan with a new fan of FRP blades, then definitely your simple payback period is near 6 to 7 months. So go with this, all the opportunities which is having for the our fan. Now, next component, that is water distribution systems. So periodically clean the plug cooling water distribution nozzle. Means in COCs increases, your nozzle get clogged. So after some times you need to clean it so that water distributions and atomizing processes are happening at very fine rate. So all second opportunities is that old spray types of nozzle with the new spray types, means square types of now it is available in the market. So you need to change these nozzle, then install the new nozzle as and when required to get a uniform flow patterns of water distributions. Then next is very important, drift. For reduction in the evaporation losses, you need to replace the slat types of drift eliminator with low pressure drops. Means the pressure drops are also low. If you are changing the design of these eliminators, so it consumes the pressure drops. So it is also you consider in the mind that there is a low pressure drops are there, and you need to replace the air drifters, water. With the technological development and the processing of PVC, manufacturing have brought the large challenges in drift, changes in the drift eliminator, shape and possibility to make the efficient designs. Yes. So in earlier case, in the case study, we found that we are having a 1% of evaporation losses. But here you can design your drift eliminator in such a way that the evaporation is losses is comes under the range of 0.03 to 0.001. So the water conservations are there. The next, optimize process cooling water flow requirements as and when required. Suppose your vessel having a 20 KL and you are doing some chemical processes, but suppose you are changing a bed size, that instead of 20 KL you are using only 5 KL. So at that time you need to optimize the flow rate, otherwise the pump require the more powers. And as all of you know that best efficiency point is also there, so you need to refer the characteristics curves of the cooling water pump, whatever we are using. Then optimize a blowdown rate as per the COC. Yes, definitely it is required. COC improvement, yes. Water conservations, sometimes people are not operating a blow down pipes or the blow down valves, because in most of the industry blow down valve is a manual operated valve. So whatever the technicians are there which is responsible to operate this valve, sometimes not operating on the regular basis, so that sometimes COCs may get increases and which can choke your nozzle. So instead of that, to avoid this kind of the operational troubleshooting, you need to use the automatic blow down systems, so that it can be regular interval, it can be blow down some of the water and it cannot create other problems in the systems. Cover the hot water basin to minimum the alga formations. Alga, all of you, we know that it is very famous. Sometimes howling is also contribute to for that loss of the heat transfers. Yes, important is monitor L2G ratio, cooling water flow rate with respect to design as well as seasonal variations. Suppose whatever the cooling tower you purchase from the manufacturer, it has supply with some standard design parameters. You need to check every L2G ratio, which is near to the rated one or not. And seasonally it is vary. So according to your catalog or according to the operation process, which is suggested by the manufacturer, you need to do some variations in your operating conditions. Monitor approach effectiveness and cooling capacity for continuous optimizations effort as per the seasonal variations and load size variations. Every times you need to take a reading of the different cooling water in, cooling water out, as well as the ambient air temperature, and basis on that you need to monitor the approach and effectiveness, so that you can have clear continuous idea that whether your cooling tower is running with a given load conditions or not. Possible improvement on the cooling water pump with respect to efficiency improvement. Definitely, with the help of the different types of characteristics curves, you need to go for the improvements. Yes, this is very important. People are avoiding uh, these points. Follow the manufacturer's recommendations, clearance around the cooling tower, and relocate or modify it. Suppose whenever you are installed the cooling tower, there where open space are there, there is a circulations of water, wind speeds are maintained. But after certain period of time, suppose your plant get expand and you don't have a fresh amount of fresh air which is comes to the cooling tower. So in these kind of situations, you need to relocate the your cooling tower. Segregate, yes, this is very important, and this is last point of the today's energy saving opportunity, but it is very important. But suppose I have designed the cooling tower to accommodate a heat load of only the our process utility. But after that, suppose I installed the DG set, I have installed the different furnace, different air compressor, and I have merged out the all the cooling systems in same cooling towers. It means merging of different activities, but it not suggests, because one cooling water temperature increases may increase the air compressor, means the increase the compressor power by 2.7 percentage. It means 1 degree drop in water temperature give the heat saving of 5 kilo per watt in the power plants. So it is very important. You cannot merge, separate the different loads, because sometimes high load is there, sometimes low load is there. Okay. So thanks. It is ending from my sides.
If anyone has any question, they can
Yes.
write that in the chats. If anyone has any questions, they can write that in the chats. We will answer it. Kunal sir, we have a question from Bhavin Makwana that please explain the flow pattern of cross flow and counter flow CTs.
Okay. Okay. So actually, I'm using the different schematics over, because it took too much time. So I have shown you schematics of that cross flow as well as the curve.
Next question is, what is the difference between mechanical and induced draft?
It is one mechanical draft is having a sub two types of that cooling tower, that is induced draft and forced draft. So it is a one part of mechanical draft.
Right.
Both are types of mechanical draft. Actually, mechanical draft means we have used the different elements like a fan or blower to having a draft of the means movement of air.
Right. Another question is from Vidhi Rotiwala that normally the range of cooling tower evaporation losses is considered more than 50%. Can we justify this? Is there is a thumb rule or something?
Okay, definitely. Students have these questions in mind because they don't know the government regulations. As government is published the rules in 2050 that no one can permit more than 3.5 meter cube per megawatt hours. It means if you are producing a 1 megawatt hour power, then you only have to consume 3.5 meter cube of waters. So this is not in the range of 50%. It is depends on your COC. Yes.
right?
Hmm.
No. When the work done is same, how will we save the power when we use FRP fan compared to aluminum fan in cooling tower?
Sorry.
When the work done is same, how will we save the
Hmm.
power when we use FRP fan compared to aluminum fan in cooling tower?
Okay, okay. See, what exactly happening whenever you have a aluminum and cast iron blades, you replace this aluminum and cast iron blade with FRP. So the weight of blade is reducing, and as your weight of the blade is reducing, your power is reducing, and you get the same amount of outflow. Means flow of air is remains the same, but for the same flow of air, the power consumption by the using of FRP blade is less compared to the blades which is made of the cast iron and aluminum. I think I justified these answers to these
I
questions.
hope you got your answer, right?
Yeah, yeah,
After moving on to the next question,
yeah.
uh, so Mr. Rohit Verma asks that if I am having old civil type cooling tower in which I don't have manufacturer data, then how can I
Hmm.
increase my efficiency of cooling tower?
Okay. It means see what basically as an energy auditor, what I suggest that you cannot use the nowadays you cannot use the low means old type of the civil construction types of the cooling tower. Instead of that, my suggestion is that you need to replace with a induced draft cross flow cooling tower, so that you can have a payback period within the range of 1.6 means 1.5 you can to the payback this. So my suggestion is that better is that you can replace the cooling tower, so you can have this opportunity to energy savings.
Next is what is the fan blade degree in summer?
Okay, so this is good questions. As I mentioned in the energy conservation opportunities, that you need to modify your blade angles as per the your conditions, weather conditions. So again, there is a questions. If you go in some, I cannot give the particulars that it is you can operate at a 13 degree. It is depends on so many parameters. Like first is weather conditions. Second, which kind of the fan that you are using, which kind of the material is used for the blade manufacturing, means blade material. And third one, very important, is your characteristics curves of fan. So based on this, you can decide whether you have to change your blade angle at which degree in summer as well as in winter. So you need to go and you need to do the exercise based on whatever the parameter. And furthermore, if you need any of my help, then I provide my contact details on a slide so that you can directly contact me if you have any problem.
Right, right.
Thank you, sir.
Yes. The next question is what is preferred, forced draft or induced draft?
It is again, I cannot give the direct answers that you go with the forced draft or the go with the induced draft. But generally, whatever the industries I come across, they definitely use the induced draft cross flow fan, cross flow cooling towers. So better is that you cannot go with the forced draft. Instead of that, you can go with the induced draft.
I think it totally depends on the application. What?
Yeah.
Right?
Definitely. Yeah.
Yes. Yeah, moving on to the next question. So, what is the use of drift eliminators?
Okay, good questions. Drift eliminators are used. It is a main component of the cooling tower, which is reducing the evaporation losses. Means whatever the waters are carry with the air, it can be collected and it is comes back into the cooling tower. So it is reducing the evaporation losses. Okay, I think I give the answers to these
Yes,
questions.
I think
Yeah.
if anyone wants the PowerPoint presentation, sir has mentioned his email ID.
Yeah.
You can ask sir to mail you that, right?
Yeah, definitely.
We have one more question, sir.
Okay.
Inline water cleaning technologies for cooling tower. What are the different techniques?
Okay, nowadays the people are using this kind of technology in which the different chemical dosings. It is a see, basically the cooling towers is looked by the mechanical engineers as well as chemical engineers, because chemical means mass diffusion process is also there and water chemistry is associated. So the inline the cleaning systems is that means you need you dose some amount of the chemicals as per the or as per the quality of water that you are circulating in the cooling towers. Based on that, some amount of chemicals are available and it is suggested by the chemical engineers. So you need to dose that and it is clean your nozzle in with the circulations of water. So this is a technology that nowadays people are using.
Right. And next question is explain cycles of concentration.
Yeah, cycle of concentration is one of the parameter which is used to reduce the evaporation losses. So evaporation as well as blowdown losses. Cycle of concentration, it means the TDS of fresh water and TDS of the blowdown waters. So ratio of that two is called a cycle. Means how much cycles. Suppose I have 30 TDS in beginning. After certain rotations, I found the 60 TDS. So 60 divided by 2, it means I have a 2 COC. Suppose I have reached to the 90 TDS. As water circulated, your TDS get increases. So whatever the TDS are currently faced and the makeup water, based on that to ratio of TDS, you can justify, you calculate the COC. And currently, for the power plant, actually I'm not taking power plant component for the cooling tower over here in the presentations, but in power plant, after certain COC, your water consumption cannot be reduced. Means suppose you start from the 2.7, then suppose in one of the my case study, I'm saying that you reach to the 7. But after certain range of the COC, the water consumption cannot be reduced. It is steady at that point. So it means it has some decreasing type of curve and then flatten curve. So up to certain COC, after that you don't go this vestige of COC. So you have to plot the curve, and based on the curve, you need to take the decision that what up to what COC you have to go and for the water conservations.
Correct. Perfectly.
Yeah,
Right. We have 2 to 3 more questions now.
yeah,
We
yeah.
won't be taking up more questions, right?
Okay,
Uh,
okay.
uh, One is as RPM and current graph of motor shows power requirement. If I
Hmm.
change my blade material from aluminum to FRP, then
Hmm.
the power requirement will be same as RPM in dual motor speed. Is there any justification to this?
Uh, actually, see what I show in case study 3, that I'm not doing any kind of the modifications in my simple just I suppose I want to give the answers in one line, then you need to learn the concept of variable frequency drive. It is an electrical types of fundamentals. So mechanical engineers cannot easy to understand that VFD drives. So I recommended that persons that you need to go with the VFD drives concept so that you can easily understand how it is reduce the power
Yes,
requirement.
exactly. And you have to also search for fan power engineering as well as
Yeah, yeah, yeah,
electricals for the variable frequency drive, so that
yeah, yeah,
you will get a better understanding of how the fan motor along with the assembly works on it, right?
yeah, yeah, definitely.
Yes. Moving further, what is the life of drift eliminators?
Again, it is I cannot directly give the answers. It is depends on the rate of water flow, material made, as well as the quality of water. So it is depends on three parameters. And if you go for the different manufacturer, they will provide you the standard life of the drift eliminators.
Last 2 questions. First one
Yeah.
is how is water circulated throughout the dry cooling tower system?
Okay, good questions. The dry cooling towers, suppose I have used the one chemical that is H2SO4 for any particular reasons, and I want to cool down that H2SO4. So I cannot directly spray the H2SO4 in my cooling tower, because Whenever the evaporations are take place, some amount of H2SO4s are comes out from the with the air. So it cannot permit us to use directly. So we need to use the different heat exchange type of devices. I cannot directly say that it is a heat exchange type of devices. It is a coil type devices in which the H2SO4 circulated, and outside of that the water, normal water is circulated. So it is indirect types of contact between water and H2SO4. So this type of cooling tower is called as a dry cooling tower systems.
Right.
Yeah.
And the last question for today is, how can we run the chilled water plant if fan of cooling tower suddenly stops working?
Okay. See, fan is provided to assist the flow of air. If your fan is suddenly get not means it is suddenly get chopped or it cannot be worked, then you get the less amount of range and your approach get increases. It means your cooling tower performance get decreases. So after
Hello.
it is not working, you can run the cooling tower without fan also, but you have less amount of performance.
Right. So, if anyone has any further questions, they can ask sir on his email ID. He will mail you the presentation if required. Right.
Okay. I share the one link over here regarding with the feedback to this
ते आपण खोकतोय.
webinar. So one can give the feedback so that
Sure, sir.
I am providing this in a chat box.
माझा तो
Till then, I would request Mr. Siddharth Vyas to please join the session and give a vote of thanks for the wonderful session that Krunal sir has given. Siddharth, can we hear it from your side? Okay, sir has provided the link of feedback form in the chats. Kindly go through it, give your feedback, and we will be up for a good seminar tomorrow. Right? I would like to thank Mr. Krunal Kheraiya sir for the wonderful and interactive session with the students and all the participants present. Thank you, sir.
થેન્ક યુ સર.
કુણાલ સર, થેન્ક યુ વેરી મચ. થેન્ક યુ
બહુ દિવસે સાંભળ્યા તમને.
સર. શું કરીએ, લોકડાઉનમાં લોક થઈ ગયા છે સર. By the way, thank you very much for nice presentation, sir.
Thank you.
Thank you all the participants for joining. Please be present for tomorrow's session right at the time. I would request Rajendra sir to please end the meeting.
Okay, dear.
Okay, sir. Thank you.